Mass is the position of the average of all the mass of an object or system. So if we looked at an object such as a hammer, this end has more mass than the handle, and so the center of mass tends to be closer to the head, so its balance point is here. Well, about there, right there. So if I was to throw this object, it won't rotate about its center, it will rotate about its center of mass. A rotating object will act as if all of its mass is concentrated at the center of mass. In this case, the center of mass follows a parabolic path. The same thing with this object right here. This is the center of the object, but the center of mass, there's a weight in here, the center of mass is offset. I can actually balance this right there on that point where I can almost balance it. Here we see the center of the object indicated by the black dot following a non-parabolic path. But when we look at the dot at the center of mass, we can see that it actually does follow a parabola. An object is stable when its center of mass is located over its base. In this case, with friction, if the center of mass is not over its base, the object will topple. Can you tell which object is not stable? What about an object with infinite sides? In general, an object with a lower center of mass will be more stable. Which of the objects located on the ground would be the most stable? Picture where the center of mass is for each letter. What will each letter do when we turn gravity on? So what is the formula for center of mass? We can use this as a vector. We can say that's the position from an origin to the center of mass is equal to m1 x1 plus m2 x2 plus m3 x3 plus all the little masses added up divided by m1 plus m2 plus m3 plus all the masses. So this is the masses at their position over the masses, the total mass. So I'll show you an example of a problem like that right now. So what is the center of mass of the Earth-Moon system? So let's draw ourselves the Earth, and the Moon we'll put out here. The moon is about 30 Earth diameters away. The mass of the Earth is 5.97 times 10 to the 24th kilograms. And the mass of the moon is 7.35 times 10 to the 22nd kilograms. And we would expect the center of mass to be much closer to the Earth, but where exactly is it? Well, to find the center of mass, the first thing that we need to do is choose our origin. And what we're going to use as the origin is the center of the Earth. So in this line right here, this will be our x-axis. What we're going to do is find xcom using the formula m1x1 plus m2x2 all over m1 plus m2. And we're also going to need to know the distance between them. Now the eccentricity of the moon's orbit is 0.055. It's pretty close to a circle, close enough for our purposes. The average distance between these is 3.84 times 10 to the 8th meters. So now we can just put our numbers in. So what do we have? We have, that's our zero coordinate. So that's going to be 5.97 times 10 to the 24th kilograms times 0 meters plus 7.35 times 10 to the 22nd kilograms times 3.84 times 10 to the 8th meters. And all of that is divided by the total mass. It's an average, so we have to use all the mass. And if you do the math on that, which I've already done, that comes out to be 4.67 times 10 to the 6th meters. Well, that's from the origin. Well, how far out is that? Well, the radius of the Earth itself, from here to here, is 6.37 times 10 to the 6th meters. So 4.67, that's about 3/4 of the way out. So the center of the mass of the system is right here. So the moon doesn't really orbit the Earth. When we look at the Earth-Moon system, both the Earth and the moon orbit the center of mass of the Earth-Moon system. So that means that the Earth is actually making a circle around this center of mass, and the moon is making a circle around the center of mass, not around the center of the Earth. Here's an animation of the moon and Earth orbiting. It may appear as though the moon is orbiting the Earth, but actually it's orbiting the center of mass of the Earth-Moon system. If we zoom in on the Earth, we can see that the Earth itself is actually orbiting the center of mass of the Earth-Moon system. By rotating the animation and looking from the top down, we can actually see the circular path that the moon is taking. If we look more closely at the Earth, we can see that the Earth itself is rotating around the center of mass of the Earth-Moon system. Here's the question. Find the center of mass of this object. This object has uniform density. So that means that the center of mass, we're going to break this up into 3 different objects. The center of mass is located at the center of this sphere, at the center of this bar, and at the center of this sphere right here. And we would suspect, since more of the mass is down on the right-hand side, that the center of mass should be to the right of the center of the bar. So let's actually calculate it. And we're going to use the formula R-com, and that's equal to m1 x1, m2 x2, m3 x3, divided by all the masses added up. And the first thing that's very, very important in these problems is to choose an origin. Now, you can pick the origin wherever you want, but the vector that's going to lead you to the center of mass is going to be from that origin. So we can kind of make life easy for ourselves by picking the origin at the center of mass of one of the objects. Different problems, sometimes, particularly with the integration, it makes a big difference where you pick them. But in a problem like this, it doesn't make as much difference. So I'm going to make that the origin. That is position 0, 0 meters. And now let's add up all of the objects. So we have m1, x1. So the first object is 5 kilograms. And its position, it's at the origin, is 0 meters. Plus m2. So that's going to be the bar. That's 2 kilograms. And what's its position? From the origin, 6 meters. So that's 3 meters here. And then we still have a half a meter, half the sphere there. So that's going to be 3.5 meters. Plus, we've got the third object here, the sphere, from the origin. It's 10 kilograms. From the origin, that's 6 meters, plus a half a meter, plus half of this, that's 1 meter. So that's going to be 7.5 meters. And this is how it's an average. We're putting all of the positions times their masses divided by the total mass of the system. It's 10, 2, and 5. So that's going to be 17 kilograms. And if you do the math on that, it comes out to be 4.82 meters. That's in the I-hat direction. These are all x's. So where is the center of mass? Go back to here. We go out 4.82 meters in the I-hat direction, and our center of mass is right there. This problem's a little bit more difficult because it's in 3 dimensions, but it's still the same formula, the same physics. First of all, to visualize this, we have an XYZ plane. So this is the X direction, this is the Y direction, and this is the Z direction. So this sphere is not above this. This is on the same height. These 3 are all on the same height. They're on the bottom, y equals 0. Okay, only this one is above it. However, this one is back in space. So what's the first thing that we need to do? Well, we need to choose an origin. And for this origin, I'm just going to pick this point right here. And that's going to be my 0, 0, or in 3 dimensions, so 0, 0, 0. And let's first figure out the vector in the x direction. We'll call that x-com. So that's going to be, our formula is m1 x1 plus m2 x2 plus dot 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 over m1 plus m2 plus dot dot dot. So let's look at all the objects. So we have, let's start with this one here. We have 10 kilograms. And how far is it from the origin in the x direction? Well, it's at 0. How about this object here? it's 5 kilograms and it is 3 meters away. And this object right here is 5 kilograms. And how far away is it in the x direction? Well, if you visualize this way, it's still 3 meters away. And then lastly, we'll do this one here. This is 5 kilograms. It's above this, but in the x direction, it's at 0. So that's 5 times 0. Okay. And then what's the mass of the entire system? 5, 10, 15. It's going to be 25 kilograms. And let's see. I did the mass here, or the math here. XCOM is a vector. And that's 1.2 meters I hat. If we do this for the y direction, YCOM, that is going to be 10. It's at 0 height in the y direction, so that's 0. Plus 5 kilograms, oh, that's also has no height. This one also has no height, but this one does. It's 4 meters up, so that's going to be 5 kilograms times 4 meters. Again, it's an average. You're averaging it for all the mass. That's out of 25 kilograms. So YCOM comes out to be 0.8 meters up in the positive j hat direction. And then we have ZCOM. And you can pretty much see that only one of these is in the z direction. I'll write it out anyway. So that's going to be 10 times 0. This one has no z direction, so that's 5 times 0. This one does. It's going to be minus, it's back, 5 kilograms times 2 meters. And then this one also has no z direction, so that's 5 times 0, all divided by 25 kilograms. So our ZCOM is equal to negative 0.4 meters, and that's k hat, in the negative k hat direction. So where is our center of mass? If we start from our origin, we would go 1.2 meters out, I hat. Then we are going to move vertically 0.8 meters, move up 0.8 meters j hat. And then we have to move back into the page, negative 0.4 meters. So that's going to be that way. And then what's our resultant vector to get to that? From the origin, that vector, r, com, is leading us to the center of mass here. And you can look at this animation to sort of visualize this in 3D.
Break the dawn and your phone just blew it up cause I rang the tone. Now you're totally suited up and the game is on, so you're coming to do me up cause it's crazy wrong. Cause it feels nice, real nice, the way we do, the way we